Alright, let's talk about that kinetic molecular theory of gases that we opened this chapter with. If you remember, our basic premise in the kinetic molecular theory of gases is that gases are constantly moving. They're these little particles, they zip around in space until they smack into something, and then they apply a force to that thing. That's where we get gas pressure from. Is that force exerted by the smack of the gas particle against the sides of the container or whatever else it's hitting. And then it bounces off and it keeps moving until it hits something else. Well, if we think about what's happening there, and we think about the energy, the kinetic energy of gas particles, if you've taken physics before, you've seen this equation. It might have looked a little bit different, just because sometimes they don't include that, Na down here. That's just the number of molecules. So normally it looks like the kinetic energy is equal to 1/2 the mass times the velocity squared. We're using U instead of V, but we just plug that little Na in there just because we have a whole bunch of little particles, not just one. And so this is the kinetic energy of all the particles in that system. It's 1/2 times the number of particles times the mass times the velocity squared. So if you think about all the gases that you can have in a mixture, you can have some gases that are very, very small, some gases that are larger, and yet, again, we don't actually care that some of the gases are large and some of the gases are small. And that shouldn't really make much sense when you think about this equation here, because this equation is telling us that the kinetic energy, the amount of energy that something is going to exert when it smacks into something, is proportional to its mass. So if you have a really big molecule like sulfur hexafluoride, which is a gas, it is probably 100 or so, maybe 150 times the mass of hydrogen. And yet, if you put a mole of sulfur hexafluoride into a container, it's going to have the exact same pressure as a mole of hydrogen, even though it's 150 times the mass. How does that work? How can you have a particle that is 150 times larger than another particle, both of them smack into the walls of the container, and they both apply the same amount of pressure? Well, the answer to that is the other part of the equation. It's the velocity. Because things that are larger, gases that are larger, move slower. And they move slower directly proportional to the amount of mass that they have. The larger the mass, the slower they move. And so, well, I shouldn't say it's directly proportional, and it is related. They work out so that the kinetic energy is always the same, regardless of the mass of the particle. If something is very, very large, like sulfur hexafluoride, so it's like a NFL linebacker, it's not going to move very fast, whereas hydrogen gas should be like a 3-year-old toddler, very, very small compared to the linebacker. Well, the linebacker, even though he's much bigger, if he was a gas particle, he'd be moving way slower than the toddler. Now, obviously, in reality, the toddler does not move as fast as the linebacker, but analogies always break down eventually. But you can think of it that way, where the larger the particle, the slower it moves, and so even though the hydrogen gas is teeny tiny compared to sulfur hexafluoride, it is just zipping, it is just booking it. And so not only does it have a higher velocity, and so it has a relatively higher amount of kinetic energy because of that, but a single hydrogen molecule might hit the walls of the container 3 or 4 times during the time period that it takes the sulfur hexafluoride to make it to the walls of the container once, and hit the container once, just because it's moving faster. So the mass is not everything when it comes to the kinetic energy. You have to take the velocity into account as well. So lighter particles move faster on average than more massive particles, and this is the equation that you can use to actually determine the root mean square of the velocity of a particle, so it is related to the molar mass of that particle. Now, I did say that it is the average velocity, and I said that because you will actually find some really heavy molecules in the gas phase that will move faster than other really light particles in the gas phase. But on average, if you take a whole bunch of them and average out their velocities, the lighter they are, the faster they go. So hydrogen, sure, you have a few down here that are really, really slow. Maybe you have some here that are a lot larger, the water molecules that are faster, but the vast majority of the water molecules are down here, whereas the vast majority of the hydrogen are way up here. So on average, the velocity of lighter molecules is faster. But that doesn't mean that every single particle is going to move faster. All right, so moving on. We've talked about how gas particles theoretically should behave. Now we are going to talk about how gases actually behave. Reality versus what we would like to think is actually going on. Because up to this point, I've mentioned that, especially at the beginning of this chapter, I mentioned that we were making some assumptions. And I did mention that there weren't terrible assumptions, and they really aren't. They're pretty good assumptions. But we do have assumptions. So, for example here, when we look at the molar volume, up to this point we've just said that gases, if they're at STP, they're going to have a volume of 22.4, we had just cut it off at the 4 before, but technically 22.41 liters per mole. And when we actually look at some gases, nothing's way off of that number, but they are a little bit off, some of them anyway. So chlorine, for example, is actually the farthest off out of all those that are listed here. And it's still 22. It's 22 something. So again, not way off. It's not like 15 liters per mole. But it is different. So chlorine, 22.06 liters per mole. CO2 is closer by a good bit. It's 22.31. Ammonia is actually really close. Same thing with nitrogen. Helium is essentially perfect. It is a very much ideal gas. And then hydrogen is really, really close as well. So you can see here that for the most part, the gases are pretty close to being ideal in terms of the way they behave. But there are some that are a little ways off. And the reason for this is because the two assumptions that we made at the beginning of this chapter don't always hold up. So if you remember, our two assumptions were that there was no attraction between gas molecules, and we also assumed that gas molecules didn't take up any space. And these assumptions break down when we have really low temperatures and really high pressures. So we're going to take a look at both of those individually. So if we're at low pressures, then what happens is the gas particles are very, very far away from each other. There's lots and lots of space. And so in terms of the grand scheme of things, it pretty much is that the gas particles occupy no space in the container. Obviously, again, that is an assumption, but if it's a really, really low pressure system, the percentage of the container that's occupied by the gas particles is minimal, to say the least. However, if you get a really high pressure system, so you've really just crammed those gas particles into the container, you've smashed them in there so tight together that now they actually do occupy a significant portion of the gas volume. And by significant, I don't mean like 50% or anything. It's still probably less than 5%, if even that. Actually, that percentage is probably even kind of crazy high. It's still a very small overall percentage, but it is enough that it's going to throw off your numbers to where you might want to actually take that into account. And so you can see that here with argon. As you increase the pressure up to crazy high pressures, these are really, really high pressures, 400, 600, 800 atmospheres of pressure. Like even high pressure systems, like high pressure gas canisters that you can order from companies, they don't go up to 800 atmospheres. Like that is really, really high, especially at 500 Kelvin, because that's a really high temperature as well. So they've kind of maximized the variables here to get the biggest difference possible, but you can see that it does vary. So the red line here is how an ideal gas would behave, and the green line is how argon actually behaves. So it is different. The two are different, but mainly just at high pressure. Down here close to where we work, close to 1 atmosphere, it's pretty much the same. We don't really have to worry about it. If we want to take that into account, if we do actually want to account for the fact that the gases behave non-ideally at high pressures, we can essentially tack on an extra little bit to the ideal gas law, which is shown right here. So if we tack on this little thing here, so this part is the normal ideal gas law. Sorry, I kind of crossed out the volume there. So the volume is equal to that. This is the normal ideal gas law, and we can add N times B to that, and that will account for that little extra bit of difference. The N here is just the same as this N, it's just the number of moles, and B is a constant that will have to be given to you in one way or another. Usually there's just a table of them because it's a constant that is specific to a molecule. Similarly, when you're at high temperatures, because the gases are zipping around really fast, when they bump into each other and when they bump into the walls of the container and other stuff that they might run into, they have enough energy that they don't really interact with each other very much. They just kind of smack off of each other and they collide essentially elastically, and they go off and they do their own thing. However, at really low temperatures, the gases are moving slow enough that when they bump into each other, they kind of stick for a second. They don't bounce off of each other like billiard balls. If you've ever played pool before, and you hit the two balls together, and they pretty much just, as soon as they come into contact, they just kind of, and they knock off of each other, and they collide elastically is what we would call that. But if the gas particles are at really cold temperatures, they're moving slow enough that they do actually kind of stick together a little bit. Because there are actually attractive forces between all particles in the universe, actually. And it's not gravity that I'm talking about, although that is there too. There are things called dispersion forces that actually do want things to kind of stick together a little bit. And those will try and hold the gases together, but they really only come into play at really high temperature, at really low temperatures, when things are not moving very fast, so they don't have very much energy, and so they kind of stick together a little bit longer than they should otherwise. And so because of that, as you can see here, an ideal gas would be this red line here, and as you get to colder and colder temperatures, the xenon, which is normally very, very ideal, as you get to those lower temperatures, it acts less and less in an ideal manner. And so if we wanted to take that into account as well, we could, again, just with a little addendum onto the ideal gas law. So in this case, we would be subtracting A, which is another constant, which again is specific to a molecule. So there would be tables with the constants for these molecules, and then N over V squared. And again, the N here is the same N as this, it's just the number of moles. V is the volume. So if we combine those together, we get this kind of nasty looking thing that really actually isn't all that nasty. It's just really a lot of busy work. Because the only new things we've added in here is the A and the B, which we can get from a table like this. And it's just a bunch of algebra from that point, which again is just busy work that you should be able to do, but I'm not interested in making you do that. What I'm more interested in is you being able to tell me when these different situations come into effect, essentially. So when we have to worry about non-ideal behavior. So in a nutshell, I expect you to know that at high pressures, our assumption that gas molecules don't take up any space breaks down, and I expect you to know that at low temperatures, our assumption that there's no attraction between the gas molecules breaks down. That's really what I want you to know from these slides here. All right, there's one last little thing here at the end that actually I meant to just delete out of here because it's super confusing. Even for me, I have to stop and think about it for a few minutes before I actually understand what's going on here, and it's not really all that important anyway, so we're just going to not worry about these last two slides. So that will be it for Chapter 9. Make sure that you get to the homework for Chapter 9 done fairly soon while it's fresh in your mind, and I will see you all in the next chapter.